Well, welcome everybody. Hopefully you're in the right session. This is a presentation about using concepts. This is a two-part session, so 3 hours of total time. So I think we'll go ahead and get started here. So this talk is motivated by the fact now that we have C++20 concepts finally available to us in real compilers and real setups. And so for those of us who've been participating in C++, we know that concepts have been around for a very long time, but having the tooling and the first class support means that it's a very different world that we are now in, and we're able to do things that we were not able to do before. So, oops. So just a little bit about me. If you don't know me, I've been working on C++ stuff since 1998. Are you not getting audio? I've seen Ray's not getting audio. Are others getting audio? Okay, so Ray, you may just need to reconnect or something. So for those who don't know me, I've been working on C++ since 1997, 98 in one form or another. Currently, I work as part of the library working group, assistant chair. Previous to that, in the mid-2000s, I worked on the chrono proposals and some of that stuff for C++11. So I've spent an unreasonable amount of my life working on C++, I would say. The goals of this talk are pretty audacious, but before we do that, let me see if I can try this. You should be getting a polling request. And so let's see if I can get you all to answer the poll. Is anybody seeing the poll? No? Okay, so the polling didn't launch. So the question I was asking there is, how many people are actually going to be able to use concepts in their day job? So yeah, the polling didn't seem to work, so I guess we'll go on without that. So the goals of this talk are I would call it audacious. We want to walk our way up the concept ladder here in terms of complexity, from the start of what is a concept, how does it actually realize in C++, all the way to how do we actually change our design practices? Do the design principles of solid and legacy design patterns even apply anymore, or how do they apply? So, oh, now I got the poll. So maybe you're seeing the poll now. There we go. Okay, cool. So one of my concerns about this talk was it's a talk for no one because no one can use concepts in their day job. But it sounds like 55% in the future and so forth. Now, I don't know. Okay, I'm just going to go ahead and end that. So the talk goals are relatively audacious in my view. We're going to walk up this ladder together from the very beginning of this. So if you've watched any other concept talks, you know that some of the advice is that you should probably just use your own concepts or use concepts that aren't your own. But I think it's time for us to break away from that. We need to get the community able to use concepts. And so that's one of the goals of this particular talk. I promise I'm not going to make you a language lawyer in this talk. We're certainly going to talk about some of the complexities here of using concepts, especially when we get to the second part of the talk. So the first part of this talk is really going to go through these first 4 sections up to reading concepts, and then writing concepts and designing with concepts are the second half of the talk. So if you're going to stay for the whole talk, then those writing and designing pieces are the secondary part. So in that part, well, let me go to the next slide. We're going to talk about some additional things. So the first part of the talk, we're going to just go over what concepts is, concepts versus types, how we use concepts in code. The using concepts in code is actually quite a long section. So even if you're not able to write your own concepts, there's a lot of ways that they can actually be used, and using the standard library concepts. And I feel like in the concept talks that I've seen before, this point was something that was not necessarily brought out as much as some of the other things. And then we'll look at how to read them. So even if you're just using standard library concepts, you want to have at least a little bit of an idea of what they look like, because you will become dependent on them, and you'll be wanting to at least understand what these requires expressions and clauses look like. And then part 2, we sort of dive into writing concepts, looking at more details about subsumption and how concepts are actually evaluated, and then some conversation about the good versus bad concepts. What is it that would make a good concept versus a bad concept? And it's my impression that really we're still, in a way, we're early on, even though concepts have a long history. I think in practical application code, we have very little concept code that is anything other than macroized stuff from the 2000s at this point. So I think it's going to take us a little bit more time before we get a lot more projects that are using it. So I think that's where we're at, but hopefully this presentation will help people move in that direction. And then I'm going to talk about designing with concepts, and this is really the most abstract part of the talk. I'm going to roll you all the way back to what is design, because I think we have to ask the fundamental questions before we can actually see how concepts fit in. And I'm going to make the bold claim that nothing has changed in software design in the last 20 years, really. So we've actually known everything we needed to know for 20 years. So we'll see how that goes and whether that becomes a controversial opinion or not. And as part of that, we're going to talk about C++ and multi-paradigm design. I'm also going to walk through serialization. The serialization pattern is an example. So in that part, we'll see, well, what would it mean to conceptify serialization? So, all right. So I'm going to show you a lot of code. And I'll just mention that we're at a place right now where certainly with GCC on Linux, since GCC 10.2, everything that I show you here, would compile and work with that environment. Some of the other environments have concepts as well. I think actually the MSVC may be more than partial now, because they're saying they're basically C++ 20 complete. Haven't tried it out, but Clang is maybe a little bit behind. Some of the standard library concepts are not there. But the bottom line is the compilers are becoming available, and we're getting access to the tooling that we want to be able to actually apply this stuff. So it's less theoretical than it used to be. All right. So with that, let's talk about the basics of concepts. So, maybe just starting out at the beginning, why do we even want concepts? Why, why do we care? Well, because, this is C++, and so we have a lot of generic code, and really concepts is built for generic code. And really concepts comes into play with libraries. And of course, we want these libraries to be fast. We want reasonable error messages, and we want something that our fellow programmers can understand. So we want to be able to write our code in ways that fellow programmers can pick up the code and maintain it and understand it. So I think it's fair to say that, template programming in one respect has been sort of wildly successful, in that it's clear that C++ is dominated by template programming in various forms. And I'm not even talking about template metaprogramming. I'm just talking about it's almost impossible to write code in C++ without templates. There are a lot of problems, though. I think it's clear that there's frustration with errors, error messages. And at the moment, the only solutions to these problems involve a lot of metaprogramming. I'll just admit to not being a huge fan of metaprogramming at the moment. I just generally don't like it. It's very, it's very opaque and weird, and the error messages, as mentioned, are very hard to sort out. So the direct language support is important to programmers in general. And in fact, Concepts is going to bring us better compile times compared to macro solutions and other SPINA and other solutions. And I promise not to mention that stuff too much. It also brings something that Bjarne Stroustrup has said many times. It brings us now to a level, and we're going to see this in the examples, where template code starts to look an awful lot like just regular code. And I think you'll see that in C+20 and beyond, a lot of the things that you might associate with templates are actually probably going to change. And the bottom line here is we want more descriptive interfaces with better dependency management. And I think it's clear that Concepts is going to bring at least that to us partially. And by the way, I should say, there was a question and answer there. So if you do have questions, go ahead and post those, and I'll definitely try to answer those. If I can't answer them, we'll take them offline and answer them after the session or otherwise. So I think it's pretty clear that Concepts isn't new. And in fact, the history of this goes all the way back to Stepanov's algebraic structures in the 1980s. But I would venture to say that, the average C++ programmer probably was not very aware of the idea of concepts in the mid-90s, say. Later on, obviously, I think it became something that was more aware. You can see in the STL specification, the original STL specification, the use of concepts, obviously not as a language feature, but just as an idea for the specification, it was clearly used. If you go back to the old SGI documentation, you'll see that information there. But even at that time, when the STL was being brought into the standard, it was actually considered, I think, fairly radical. Most of us in the late 90s were programming with object-oriented libraries that used inheritance and so forth instead of templates. And the compilers, frankly, of the day were really not up to the task of a lot of the template programming that Stepanov and others really wanted to do in the STL. But if you scroll yourself back to the early days of Boost, you'll see that the concept check library actually is circa 2000. So from that perspective, the ideas and so forth behind concepts really, and concept checking in general, aren't new. So then we have the long drawn out history to get to 2011. Originally, concepts was going to be a language feature in 2011, but of course, famously, the committee decided that it was too large and it wasn't ready for prime time. So it was pulled out, and in Palo Alto in 2011, many of the main principals that were working on concepts at the time came up with this proposal, Concepts Light, which is essentially more or less in broad brush what we ended up with in 2020. So in 2017, that Concepts Light became a technical specification. GCC got an implementation. And then, of course, in C++20, ranges library is completely specified using concept. We have other concepts that are also in the C++20 library as well. And that's based on all of that history. So it's based on 20 years of history that the concepts that are in C++20 are there. What's interesting, of course, is that as we speak, over the last few months, the C++ committee has been changing the concepts in ranges because mistakes were made. And so even with all of that history, it's sort of a forewarning that it's difficult to get this the way we actually want it. And I think that's going to be one of the interesting things we're going to see when we talk about concepts as a design tool going forward. How do we really get the right concepts without even working on it for 20 years? Ranges is specified in terms of things like iterators, which are well known. It's not something that's new at all to C++. So how is it that we could have made a mistake? Well, it's more in the higher level functions that those mistakes were made. So the other thing I'll point out here, I've got a link to the paper. There's also some references in the slide pack at the end to a bunch of other things here for further reading. One of the things, if you go watch older presentations, you're going to see Pascal case used for concept names, for standard concept names. But of course, at the last minute, the committee decided that wasn't the way they wanted to go. And so now all of the concepts are using the standard library form of snake case. You'll also see that in the old TS and so forth, the concept syntax was a little bit different. So you had to write concept bool. The committee decided, again, fairly late in the process, that we shouldn't write that extra bool. It was redundant because concepts really are a Boolean predicate. So once you know that, you don't need the bool. It's just redundant. All right. So what is a concept exactly? Well, it's going to take a while to get that all sorted out. So we're going to sort it out slowly through this whole presentation. But basically, it's a predicate. And the predicate is a Boolean predicate that works against types and can also work against values. I'm not going to show you a lot of examples in the value side, but I can see some potential uses for it. I can also say that from the experimentation I've seen and done with it, it can be a little bit trickier because the rules are a little tricky. I'm sure we're going to find very good uses for it in the future. Some of the kinds of examples I could see is, performance tuning for, certain, sizes of things, and like, oh, if it's a certain size, I'm going to use SIMD instructions versus some other kind of mechanism. So some examples of the kinds of requirements that we can write are, we can say with respect to a type, what are the required methods for this type? Or what are some subtypes or base types that this particular type needs to have to work against the function, for example, that we're constraining. So we're going to use these Boolean predicates to constrain the types that work with overloading and other mechanisms in the language. I also have this required semantics starred, and that's starred because when you listen to the folks that have worked on this language feature and worked on concept-based design, they'll say that the best concepts also enroll the semantics. But the only problem is we don't actually have a way with compilation technology, and I think there never will be, that's my take on it, a way to really know that a function, say, is order 1 versus order n. It's not something that the compiler can really deduce because of, halting problems. So short of actually being able to have an AI that can analyze the code in the compiler, I don't think we're going to see required semantics. But when we get to what's a good, bad concept, I think generally speaking, we want to know what those semantics are. So like the order of an algorithm is the kind of thing that is in the semantics. So the realization of concepts in C++, includes a couple of new keywords, requires and concept. And it also has this other syntax. I call it concept name auto. So this is a modified form of auto. And that concept name auto allows you to describe a set of types. And I'm going to show you a lot of examples of this because this is the usage part of using concepts in your own code, even if you didn't write it. And there's new rules for overloading and other things. The question is, what about axioms? So yes, there are Boolean predicate axioms, and actually I think I have that on the next slide. So hopefully that answered the question, but yes, so you can compose these Boolean predicates with and or and not logic. So your standard Boolean logic applies. And we're actually going to see examples of this again as we go along. So at the end of the story, though, this Boolean predicate that we're going to write into our code is going to be used to classify types. So we can say a type is either in or out of the set. We can say that a type models a concept. That's the way we talk about it. It models a concept if the predicate actually is evaluates to true. And as I said, semantics would be nice, but it's not something that's currently supported. All right. So let's just think about for a minute types versus concepts. So what can we do in C++ with types? So obviously in C++, a type, if it's a built-in type, has a set of built-in operations. If it's a type that we create with a class or a struct, we can describe that type, all of the operations that apply directly to that type. That type will also include, for example, data members, which actually describes a memory layout. So there's sort of an implementation aspect that's very specific with types that we get. But we also describe relationships with types. So we have base classes, for example, or if I have a type that has a declared dependent value, so it's a member of a class, for example, those are relationships between types that we declare and can see in code, and that builds dependencies into our architecture. So the concept, on the other hand, also has facilities for describing types. Because if we're going to do predicate logic about a type, we have to be able to describe the form of the type. And it can do almost all of the things that a type can do. In fact, it can do some things probably that a type can't directly relate. But on the other hand, it also for sure does not describe a memory layout. So that is something that's very different than a type. The concept never defines how memory is laid out and how the type actually would come to be. So just from that basic setup, we can understand that a concept is going to be something that's a little bit more abstract than a type. And I'll also mention that whether we like it or not, the way we describe these relationships between types with concepts is different than how we describe them with types. There's some similarities to that, but the syntax is relatively different. So it's something you have to get used to in terms of how you express what is part of the type or part of a concept, sorry. And the other thing I would say about the concepts is you can have sort of an abstract description of a type which doesn't care about certain aspects of the type. So for example, I might say that a particular type to model a concept has to have a particular member function, but I don't have to necessarily describe its return value. So I can do some things that I can't actually do with a type. All right, we got 15 slides in and we finally get to look at some code. So this is a simple one parameter concept called printable. And my goal here with this particular concept is to just describe a type that requires a constant print method that takes an OStream reference and then of course would emit the data members into the OStream. So it's very simple. My type here, very simply, it models that concept. Let me see if does this. Yes, it actually does work. I can actually highlight things. That's good. So I'm not telling you just yet what is in this requires, but that's the concept syntax that you'll see throughout. So you have a template looking function looking, but it's actually a Boolean predicate. So that's what we'll see later on. You'll also note that this is actually in a namespace called namespace IO. So concepts notably can live within namespaces, and it's good practice to do so. Since you can't redeclare a concept, you could have name clashes if you use something that's common. So it makes sense that we'd be able to do this. But it also means that we could have two printable concepts, depending on how things are set up. And at the bottom here, I'm doing a static assert against this particular concept. And the reason that I'm doing that is one of the things that's basic about concepts is they're not going to be evaluated until they're used. So if I want to make sure that my type actually models it, I have to do something active myself. And one really easy way to do that is to just static assert in the header file right next to the type to see whether or not it models the particular concepts that I think it models. So some notable concepts. The concepts are evaluated entirely at compile time. There's no runtime footprint here, which makes them very compatible with high performance template code. And as mentioned, they can be scoped in namespaces. So one thing to consider here is that if I've written a concept and I'm going to use it in my design, it means that if that concept changes, then there's a good chance that I'm going to be recompiling all my code since it's only resolved at compile time. So there's something to keep in mind is the dependency on a concept means that there's a high chance that recompilation is necessary. We're not going to get any sort of virtual function table behavior out of concepts. It's not something that concepts can do. I'm also going to talk more in a minute about this dichotomy between the idea of pure auto and a specific type. I think one of the interesting things about concepts here is that it sort of bridges the world between that. And it changes maybe how we think about modification of client code that depends on concepts. So of course, concepts is largely built, for constraining templates. That's really the primary thing to enable better generic programming through constraining templates. And that's the end of this basic section. And so now we're going to talk about using concepts. And this is a fairly long section. So even if you don't come to the second part of this talk, hopefully what you're going to see here are some examples that you can pull out of the box and actually use in your day-to-day work. And so this is more of a client's perspective of concepts. So the first question is, yeah, what can we do in our code and what can we not do? So, a few basic things. Obviously, we can constrain an overload set. That's one of the fundamental things in generic programming is we have a named function, which we'd like to overload in different ways. And concepts gives us a whole new way to set that up and do it. We can initialize a variable with this concept name auto syntax, which gives us a new intermediate way to look at declaring variables and initializing them. If we want to, we can actually use concepts in conditional compile time compilation with const x for if. So we're going to see examples of this. And we're also going to be able to use it with types maybe you didn't expect. Like you can use unique pointers and pointers. They're not really concepts of these things, but we're able to constrain types using the syntaxes here. But it's interesting. So we're gonna see examples of this in a minute. And then of course I can partially specialize a template with a concept, and this is going to allow addition and subtraction of code in certain places where I want to be able to do that in my design. And then this last bullet is sort of an interesting side effect of things, and it's not just concepts itself that allows this, but it's changes to the rules around auto that allow us to fulfill this last bullet. And I have regular code in quotes because I think it's important to understand that we're still dealing with template code, but you're going to either be very frightened or very happy, I'm not sure which, by the syntax that's going to be available coming up. And maybe you're going to want to see the word template for forever, but I'm going to show you that it's no longer necessary in a lot of code. So some things we can't do. We certainly can't inherit from a template or a concept directly. Now, having said that, we might be able to inherit from a constrained class or struct that is constrained by a concept. In fact, I'm going to show you an example of that down the line here. I think I can't remember, in the reading concept section. So that's the last part of the first part of this talk. We cannot constrain a concrete type using the requires clauses. So we'll see that the requires clauses are able to constrain lots of things, functions, and we can do that, but a concrete type is not able to be constrained by requires. That said, we can constrain the use of a concrete type in a function, for example, using concepts. So we'll see examples of all of that as well. So I said earlier, one of the distinctions between concepts and types is that there's no storage understanding by concepts. It doesn't understand that. So obviously, we're not going to be able to allocate it with new. So that's obviously off the table. And concepts aren't going to apply to virtual functions. You can't have templatized virtual functions. So they're out of bounds for virtual functions. So where can I write this concept name auto thing I keep talking about? So what I mean here, right, is I write down the concept name and then I write auto, and then I can do something with that, right? So I can write it in a variable declaration. I can write it as a function parameter. I can write it as a return type from a function. If I have a class template member, then I can write it as a template argument without the auto in that case. I can't write it as a straight line class member. That's not possible, but I can do that in a template class. And I can't write it as a base class because I can't use inheritance with a concept. And template alias parameters is another place that we can actually use this concept auto syntax. So let's look at one. So I've got my printable concept here again. Again, I'm not going to define what it is at the moment. We'll get to that. And then I got another one here, which is associative container, which, you can use your imagination what that kind of concept would look like. So given those two concepts exist in my translation unit, the following code is all valid code. Well, not quite, mostly valid code. So this first function here, f, you can see I'm now taking a parameter called printable auto with s. So anybody got an idea what is actually going on here? You can put it in the chat if you want to. If anybody's got an answer to that question, what is printable auto actually saying there? Okay, well, that's interesting. So I can write that syntax, it's valid code. So here's a more traditional case, the way we think about concepts. We think about constraining a template. So I have the concept name written here. This is the short. You say a concept is printable. Maybe not quite. That's not quite what I was looking for. Yes. Roberto has it in the chat. This f is actually a template function. And this is what I'm talking about, where sort of template code suddenly becomes regular code. Because the word template does not appear there, but this is a template function. It's a constrained template function, which will only accept something that models the printable concept. Okay, so going back to my type here, I was mentioning that in a regular class, I couldn't, if this template wasn't here, I couldn't write, a concept name for this T, but I am actually writing a concept here, right? In this particular case, because this is a template class. And in this template class, I can do that because actually, if you think deeply about it, if I just took this associative container and wrote class instead, what does it mean? Well, it means that T is really just a placeholder for a type. So at compile time, when I instantiate this template, that type will actually be resolved. And so T will then be a concrete type. So the only difference here between writing class or type name here and this is now I've applied whatever the set of constraints that are in that concept definition, to this particular type. So if I try and pass an int in here for T, it's going to fail to compile and we're going to get an error message. So at the bottom here, I've done something interesting. I've written printable auto on the stack as just a data member, or sort of a variable name, and associative container auto also. Anybody see any problems with this? Yeah, so it turns out this won't compile. And the reason that it won't compile is because this is not specifying a type, right? It's specifying a placeholder for a type, a constrained type, something that models printable. So as a result, since this is just a placeholder, I can't actually write this because the compiler doesn't know what type that actually is. It can't allocate storage for it on the stack. So what happens? Well, I get an error message. It looks something like this. And honestly, this is the error message that comes out with very little editing. It's actually a pretty good error message. It tells you exactly what the problem is here. Printable is a placeholder that's not initialized. So you can't get too much more clear than that. So I actually have to initialize this to get it to compile. And if you think about this, I'm calling some function here and it's going to give a return type. And really now what I've said is, well, this return type it better model the printable concept. And if it models the printable concept, then this will compile. If it doesn't model the printable concept, then it will not compile. And the same thing is true here with the associative container. I have to have some kind of initialization here that will actually make my map fully formed for the compiler. All right. All right, so here's another example. I mentioned earlier that it can be a function parameter or a return value. So we have a couple of functions here. This first one is written in a traditional style. So I have the word template, I have printable T. So I'm constraining it. And then I have this return value here, which is printable auto. So this is a deduced return type, but it's constrained reduced or deduced return type. So this is, again, the expansion of our ability to have compile time programming that does this. The second version of this function is exactly the same as the first one. It's just written in that different style where I've actually just removed the template altogether and written the printable right in the function declaration itself. So I've heard some commentary that, some people don't even like this style. They want to put the requires clause below the template definition, which I'll show you examples of that later, because that's a different way you can write the same thing. It is C++, so it is necessary for us to have 5 ways to write the same thing usually. That's a little bit of a joke, but it's not entirely a joke. But the bottom line here is that, I'm showing you kind of after, some decent amount of experimentation. I kind of like this kind of syntax myself. To me, this looks very readable. Once you know that auto means that, oh yeah, that's a template parameter or a template return type, essentially. Once you know those things now, you're not scared of it. Let's see. Can we return a concept auto from a non-template function? I think the answer to that is no. So yeah, you're in template land no matter what. I think by putting concept auto there, it essentially makes it a template no matter what. All right, so let's talk about overload resolution. This is one of the fundamental things that this is built for. As I mentioned earlier, there's now a whole series of new rules on overloading, which may scare you. I don't think in the end, when you start using it, it's really hard. So, my experience with it has been pretty good. Can you get overload ambiguities as a result of using concepts? Yes, you can. Ambiguity is still something that is a real thing with overloads. And so, when we get down to writing concepts, we'll talk a little bit more about that. There are cases where you're still going to have that problem. Okay. So let's take a look at an example. So I'm now writing this function called PrintLine. Okay, so once again, I'm using the shortened syntax for PrintLine here. So this is a very simple function. It takes a parameter, which could be anything. It's an unconstrained template function, is what you're looking at there. And so I have a thing called myType. And I have some, calls to PrintLine, which have, characters and an integer. And if I put this in, right, it's going to work fine for the things that have an OStream operator, which, the first 2 things do. But of course, if I put in myType, it doesn't have an OStream operator, so it doesn't know how to do that. So how can I solve this problem? Well, the traditional solution to this problem is I can overload PrintLine with myType, right? I can just write the type right here, and I get an overload that's preferred by the compiler because it's a better match than the template function, which has auto. And so, I'll get this selected, and then everything will be good. So, of course, this is sort of tedious, right? If my goal here is that I have all of my types in my system built up. I don't want to have to write PrintLine over and over and over again. That was the point of having templates in the first place, right? So, I just don't want to have to keep writing that over and over again. So how can we use concepts in this case? So let's bring back our printable concept, and I'm going to put a new concept here. And now I'm actually going to show you the requires for these. And in part, I'm going to show you that because I'm going to show you what happens when we try to use this functionality in a place where it actually won't work. And you have to understand a little bit about what it looks like to understand what the error message is showing us. So here we have the concept declaration, and we have the requires clause, and we have a couple of interesting things here. We have this ostream ref os. I mean, this looks like a function declaration, but we know requires isn't that. It's a keyword, right? So, but really that parameter list is really actually a parameter list there, and it actually behaves the way a function parameter list behaves. So you can const qualify, you can move qualify, like you can do all of the things that you can imagine in a function parameter list. So then I have these braces, and then I have a statement here, v.print.os, which looks like I kind of implemented something where I called a method on this parameter v called print, and I passed the ostream to it. So yeah, it's code, but it's actually an expression. And this will return a Boolean true if this expression will actually compile. So this concept will evaluate to true, or in other words, if I pass a type T and it has a v.print method in it that takes an ostream, then this will yield true, and the type T will model the concept printable. So that's the very simple version of it. Output streamable is really the same thing. It's got the same parameter list in this case, but I'm looking for a different operator here. And so that's a slightly different definition. All right, so how am I going to use this? Well, so for one thing, now I can actually check my types like I was showing you before. I can assert at compile time that my type model is printable. One interesting detail that might not be obvious because it's invisible in the concept definition is that if I write print and I make it private or protected, then this is not going to compile. Static assert will fail. And why is that? Well, the reason is because back here, remember, I'm basically saying, look, I got to have a public member function called print because, I can't call a private member function called print. I'm not in a context that would allow me to do that. So that's an example of some of the subtlety that's here and some of the complexity that's here. I don't want you to get down on it because of that, but it is one of the things that's interesting. Okay, so fine. So my public method, it's fine, does the right thing. And so now what I'm going to do is I'm going to use the printable concept here. And if I have the printable concept overload for this particular function, then that's going to take anything that implements a print function, and it will call p.print with cout, and then output the end of line. So now I've created an overload that works for anything that's printable. And anything that's not printable does not evaluate to true in that concept, will actually fall back on the primary template here. And if it doesn't have an ostream operator, we'll get your usual horrible error, way down in ostream's implementation somewhere with 500 lines. So I can actually also pull this up a level, and I can put that output streamable here as well. And that allows me to constrain, I don't even need a primary function template here. And of course, if I have a type like my type 2, which does not model printable or output streamable, either one, I'm going to get a compile error. And so that's a good thing. and it works exactly the way you would think it works. Okay, so that's your basic example. Sorry, I missed this question. In the last example, could the return type be T auto? And I'm not sure which slide you're referring to as the last example. So maybe if you could clarify which slide we're speaking of. I know I went past them probably. But I think the answer to your question is likely no, depending on which one we're talking about. Okay, let's move on. Let's see some other examples where I can use this concept name auto syntax in maybe somewhat surprising ways. So here's an example of, actually newing a pointer and assigning it to a concept pointer, if you will, right? So I have my printable and I have printable auto, and I'm initializing it with a new. When I first realized you could do this, I was kind of surprised. It wasn't something that was obvious to me, that would be possible. But even more interesting, I can actually say standard unique pointer of printable auto, and I can constrain a make unique call to, in fact, enforce the fact that, the type that I'm getting back from this make unique, is actually in printable auto. And so that means that I can for sure call this print function like this. Okay, so let's see. Got a couple of questions here. On the other hand, we can't write unique pointer auto, can we? No, I don't believe you can write an unconstrained unique pointer auto. That's a good question. I haven't tried it. Another question here. Suppose there are two overloads of a template function. One is more constrained than the other. How can I explicitly invoke the less constrained overload with a type that would satisfy the stronger constraint? We're going to talk about that a little bit more, the subsumption process. And I think the answer to your question is, I don't think there's a way, to actually, there's not a way to do that directly. So, yeah. Without basically concretely overriding the type. Okay, so that's sort of all for this pointer and concept thing. But what's interesting now here, right, is you can do some interesting things. Like if you've got factory functions now, you can do some interesting things here that aren't just, pure template return types. They can model concepts in your design. So what happens, like if I try to do something, that's completely outside of printable. So I have some type wherever, and I try and new that to a printable auto pointer. Well, this is actually the error message you get. And it's very, I will say, lightly edited for this slide, just so that it fits a little bit better. But basically what you can see is you see this constraints not satisfied. Okay, and you see the satisfaction of it is that printable whatever, because it's telling you that this thing needs to be printable, right? And then it tells you, oh look, with requirements std stream, v.print. Remember, that's what we wrote in that expression that defined the concept, and it's saying that this method v.print os is invalid. So that is it. That really is it. So for those who are saying that, will concepts bring better error messages? I think it's an absolute win. There's no question that in 2 seconds, I can understand what this error message is, and I don't have to wade through 29 pages of stuff. Okay, so the other question was about unique pointer foobar CTAG. Yeah, I'm not quite sure still what we're getting at there. So we'll see. Maybe that'll have to be in after the session discussion. All right, so let's move on to another place where we can use concepts in the machinery of concepts without actually using the concept keyword per se, but we're going to use a static if here. We're going to use if const expr. In C++ 23, you're going to be able to use this if const eval as well. I believe that's either in the working paper or close to it being in the working paper. It might be one final vote. So if const eval will ensure that you get compile time resolution, but you're basically going to get that here anyway. So let's write PrintLine again, and let's write it just yet another way. So I have my O stream, and I have my type. In this case, I've written it with traditional syntax. And of course, it's not constrained in any way by the template itself. It's only constrained internally now, because here what I've done is I've said, okay, if it's const expr requires printable of t, then I'm going to take this branch where I'm going to say v.print. Otherwise, I'm going to use the other branch where I try and stream it out. So this is the morally equivalent of the code that we had before. But now we've actually taken it out of overload resolution and we've pulled it internal to our implementation. So it's a different design and it has different properties with respect to extensibility. I can't really extend this, easily now by using overloads, right? I couldn't come up with a new concept that would integrate some other thing. I have to actually go change my internal implementation in this particular case. So this is one of those design trade-offs that especially in the second part, we're going to talk a little bit more about. Is this the best way to do it? Or is the best way to do it using overloading? So it depends, I think, is the answer. And it depends on what your goals are and what you're interested in. This has some nice properties. It's all right here in one function. I can clearly see it. By the way, there's a shorter syntax. I don't actually need the requires here. I can just write if const expr printable, just like I could with a type trait or something else that's compile time resolvable. And that's the shorter version of how to actually do this. So that's nice, right? I mean, this is a nice facility. If you're going to use static if for, even for performance reasons or whatever, there's lots of applications of this. So there's another thing that I can do here with the same case of PrintLine that doesn't even require me to have a concept at all, because the requires clause now allows me to actually write the requires inline. So I can actually just write that expression that we saw before in the definition of the concept right here. And that's it. Now, obviously there's a downside to this approach, which is to say that anything that becomes non-trivial, that is probably not the way we want to do it. We probably want a formal concept that has a name that's defined somewhere. We're going to see a little bit later, these expressions can get very complicated. And so, we don't want to, we don't want to get to the point where, we have some really horribly complicated expression here if we want to maintain our code base in a clean fashion. Okay, so let's look at something a little different here. So this is a case of constraining a member function of a template class that's not a template itself. Okay, so in this case, what I have here is I have a wrapper type of class, and I want to have some different behavior for this type based on whether or not the T itself is a pointer type or not. Specifically, I want to have a dereference operation if this is, if this is a pointer type, if T is a pointer type. So what I have here, right, is I don't have the concept written in the class header at all. I don't have that concept name auto, but I have this thing here, right? I have a requires clause that follows this particular operator star. And so what does this do? Well, what it means is if I instantiate this template with something that's a pointer, it means it takes this function and removes it. So essentially this function doesn't exist if T is a pointer type. And of course, this can be a very complicated expression, and I could have multiple overloads of this depending on different concepts. So this is a very powerful technique, right? This gives me a way to define what I'll call negative variability, right? So I have a certain set of types, that have this variation, or it's a positive variability, I guess, depending on which way you're looking at it from, that have this variation where they have this additional method that doesn't belong if the type is a concrete type. So what happens if I instantiate it with a pointer, I can dereference it just fine. And I get an error like no match for operator star if I do it with just a regular integer. So there's a question or a thing in the chat. So requires ... is actually a concept lambda. Therefore, I think it is useful. I'm not sure what you mean by a concept lambda. And actually, that's another interesting question. Yeah, can you apply concepts to lambdas? I think you can, but I have not actually experimented with that. So from what I know of it, you can't. There are definitely, you can constrain lambdas. Okay, so let's look at something else. Let's say, I wanted to make my vector, printable. Can I say vector printable? Well, I can't say it the way it is here on this slide. But of course, I don't want to rewrite vector so that, I can constrain vector in some way that I require it to be, the type that is held within the vector is a printable type. But it turns out I can do this, and that's by using template aliases with concepts. So it's very simple and straightforward. You can see here I have my template of printable T, and I can say using vec of printable. So I've given this type that's constrained by printable a new name. But then, yeah, I'm just using standard vector of T. But in fact, now I've created a type by externally constraining standard vector in a way that if I try to pass something into it that's not printable, it will no longer work. So now, yeah, I can declare a vec of printable of my type, and this is means that if my type isn't printable, then this is not going to compile. As a matter of fact, here's what it looks like if I try to now say vec of printable of int. I'm going to get a failure. I'm going to get, again, template constraint failure. And I'm going to get using vec of printable, so I see that constraint. Question is, are there going to be examples of concept checks involving template parameters? The answer is no, there's none in this particular presentation, but it is something that can be done. Okay. All right, so let's see. So what else here? So yeah, so I get, again, the printable of T, and again, I get exactly what happened. And again, this is just mildly edited for space. It is the exact thing that comes out of GCC 10.2. So this is what kind of error messages you're going to get. So for my takeaway again on the error messages is this is a win. If I want to do this kind of constraining of some kind of a template type externally, it makes perfect sense. All right. So now we're going to move on to the standard library, because if you're a user of concepts, you're going to want to know about these concepts. I'm going to go through this rather quickly in the sense that, we're basically 25 minutes, so I'm a little bit behind on time. So I'm going to go over these pretty quick. You can go on CPP reference and find out all about these. So you don't need me to tell you what's on CPP reference. I don't actually like the way CPP reference, and actually I think that came from the standard groups, the standard concepts per se. this whole category of core language concepts seems like it overlaps completely with object concepts and so forth. And now we have to talk about type traits for just 1 minute, because obviously in template-based design, we've been using type traits to change policy and behavior in templates constantly. And obviously type traits are a compile time thing. They're mostly just templates, but some of them do actually have some compiler magic behind them. So part of the question is, when should we favor a type trait versus a concept? And we're going to get to that more in section 2. But the bottom line here is that a lot of type traits, even in the standard library, are actually sort of augmented or replaced with concepts. And we're going to see why in the second part, why that is. But in part, yeah, it's still going to be the case that you're going to define concepts in terms of type traits. Type traits are going to still be there. They're still going to play. You're not going to see any reduction in the type trait system, probably just more of them and more of the same. Okay, so here's some of the standard concepts that apply to numerics. Not very interesting here. There's actually a bug in the slide. All of these should have a T after them. All of these signed integral ones. So fine, these are the things you expect. So here's a question, floating point T. Is that going to know about something in Boost Math Library, special number type that's some kind of extension? The answer is no, it's not. It's only going to know about the fundamental types. And so if you want to use numerics that are outside the standard library, you're going to have to build your own concept that would allow you to include those types. All right, so moving on. So quality comparable, this is simple. Does a type, is a type quality comparable? Does it have an equal operator? And our two types like T and U can, even though they're different types, are they still equality comparable? So this is something a little bit new I haven't shown you yet. So we have now here a concept, right, that has 2 parameters. So now we're actually in the world of looking at the associations between 2 different types. So what it's saying is that, T and U have an operator equal that will work. And so that's an association between those 2 types. And that gets us into the higher level discussion of architectures and types that work together. So totally ordered is very much the same thing. It just says, do I have all the various operators that I would expect? And then there's some other object relation types here. So again, we've got 2 parameters. So same as T and U, the same thing. That's handy in a lot of cases where we want to know that, oh yeah, the parameter is passed the same as something that we have elsewhere. Derived from, does something inherit from it? Convertible to, assignable from. These are all questions that you might want to be able to ask in code. Some other object-related concepts, being able to construct things. So default initializable, okay, fine. This second one is interesting here, constructible from. You'll note it's a ... It's actually a variadic. Okay, so you can ask the question at compile time, does this type T with this set of parameters that I'm passing into it actually able to construct from it? And so I showed you before where I was removing a method. Imagine you can remove a constructor from a template class if, in fact, you cannot construct, using this set of particular parameters. So you can do some very interesting things with this. And this is just to say that, like was asked in the chat, template parameters. So, template parameters and other more sophisticated template techniques can definitely be used with concepts. Question is, what's the idiomatic way to use type trait alias? Is it abstract V as a concept? Yeah, I'm not sure I follow the type traits alias. I I think what I'll say to that, and I think we'll get more to this later. I think in general, you're going to want to prefer concepts, especially like if you're doing overloading, and that's because of the way subsumption rules work. But we'll just leave it at that for now. All right, so we've made our way up the ladder of standard library concepts to regular and semi-regular. If you don't know about regular and semi-regular and why we might care about them, go watch a Sean Parent talk. There's probably a half dozen of them online. They're a very useful way to say, hey, this thing can, copy, move, default, construct, and destruct. Semi-regular is the same thing without the equality comparable. So, one of the fundamental things I might want to do when I'm programming here is I might want to static assert is regular. Because, by the way, did you remember what all of those methods that the compiler writes for you? And by the way, are you familiar with the additional things that C++20 is going to potentially write for you or not write for you, depending on what you do, right? I mean, if I add a default or I add my own written default constructor in here, this might not evaluate to true anymore because the destructor is not going to be generated for me anymore. So those rules are complicated enough. This is a simple way to check that I'm actually there. So again, what does it look like? Well, here's what it looks like, which is not quite as nice, because we have this business here, required for satisfaction of weekly equal compare underscore gobbledygook. What is that stuff? Well, that's stuff that's coming from the standard library. So maybe one limitation to the way the error messages happen is that, in fact, you get some insight into what's actually happening there. All right, not bad. Too bad though. Really, all it's telling me is I need an equal to model regular. So I write that. I can write it as the default, and it'll work fine. So this last part I wanted to mention, I want to take you up another rung of the ladder here and talk about the ranges concepts. So I'm not going to talk about all of them, but I want to emphasize the fact that the ranges concepts are there, and they're there and are usable by programmers. So in this particular case, what have I got? I've got this thing I'm calling printints, and it has this std ranges range auto, right? So that is a concept that comes from the ranges library. So I have a for loop here with auto, and I just wrote my range right in here. So it's a range for loop, and I just simply print things out. Simple, right? This is very straightforward code. What's the magic here? Well, the magic is that literally anything that models range will work with this code. So here's just an example. I can use a vector. I can use an array of int. I can use a span of the same array. I can use a C array with a span wrapped around it. I can use an iota view. All of these will print 1 to 5 and so forth. So that's actually, you can see some very powerful generic code that's written very simply just by using the standard library concepts. Okay. So we're at 15 minutes to the end of the session. We may be falling a little bit short on this section. We shall see, because I'm a little bit behind time, but let's see what we can do. So this is where we start, to get a little bit more down into what does the requires expression and requires clause do? What can we do with it? So as mentioned before, we were really looking at a requirements expression before. The requirements clause is a very much related thing. Again, it's a Boolean expression. It can be used after a template or a method declaration. So I actually showed you an example of the method declaration case. The clause or the expression can actually contain a clause as well. And yes, if you go watch some other presentations, you can get requires, as it turns out, which Bjarne Strustrup will tell you is a code smell. But in any case, you know, we're not here to go into all of the details of what you can do, but I want to give you a survey of it so that you can sort of understand it. So let's write a new requirements clause for printable. In a minute, we'll do that. But let's look a little bit at what the requires, you know, expression really is. So really what it is a sequence of requirements. It's not a single one, it's a list. We already saw this parameter syntax where we have this sort of function parameter syntax. And then it's followed by a requirement sequence. So what this tells you is the parameter list is actually optional. I don't necessarily have to have that parameter list if I don't need it. In fact, the degenerate case of this is just saying, you know, equal to true, because true is actually a literal or at compile time is available. So here's that more complicated version of the requires expression. So this is a requires expression. So I have my same parameters here, but let's say, you know, in my world, I've moved up the ladder for printable, and I'm going to intermix some capability of formatting into my print function. So now I need to require some additional capabilities of my type. So I have my member function from before, but now I have a free function called format, which can take my type, and I want to test that that's the case. So wait. Right, so it's a sequence, right? So this is the first of the sequence, the second of the sequence. These are also just Boolean expressions that are all ANDed together, because really what this is saying is I have to have print and I have to have format. Oh, and I have this standard library thing, movable, that I just showed you a minute ago. So I now make that a requirement as well. And I'm also making a requirement of the fact that I need you internal to your type to declare another type called format, because for some reason, something I'm going to do in my print algorithms or my external algorithms requires knowledge of this type. So now we can see, right, the breadth and the scope of this. I can basically express many things about the type in this syntax. Should it be requires movable T? The requires is optional. That's the question in the chat. Should it be? You know, can you say, all I can say is this compiles this way. You know, should you put requires in front of it? That's a question for your coding standards. So let me show you one other thing. And this part is where we start to diverge a little bit from what you might think of as sort of looking like standard code. Because now we have something on this output streamable thing that we had before. And on the output streamable now, we want to constrain something that we haven't constrained in the group before. Because in a true output streaming operation, right, one that's actually meets the requirements that we would expect in an output stream operation, we would expect an OStream reference to be returned from whatever that operator is. And so this is how we express that in concepts. So what it says is that this expression here, the curly braces are important here, you know, returns. So this is the trailing return type syntax. And I've used this std same as here for a reason. If I pull this off, it won't compile. You won't be able to just say std ostream ref here. You have to evaluate it as a Boolean to say it's got to be the same as this. What's also interesting, of course, is I don't have to use same as here. I could be, if I was doing something else, I could say something like is convertible to, or is inherits from, or some other kind of constraint that's more sophisticated than just same as. In this case, same as makes sense, but just so these things are very flexible, and so we can say expressions that are very sophisticated. All right, so before we've talked about we've got Boolean expressions here. We have really three things going on. We have some atomic level constraints, and we have conjunctions and disjunctions, ands and ors and nots is left off of this slide, but we have those as well. So how do those look? So here's an example of printable and streamable, or printable or streamable. And by the way, I'm just going to mention that don't write these concepts. These are bad concepts. You probably don't want to write them this way. Printable or streamable feels like a bad concept to me. And I'll explain more of that in part 2 of the talk. And you'll note here that it's the standard or syntax that you're used to. But I actually prefer writing or, which if you didn't know has been a C++ keyword for many, many years. I feel like this is more expressive. And it also distinguishes the fact that, yes, we're in a concept context here, and we're writing a Boolean expression. So we have, disjunction, conjunction, we can do that. And now, again, this allows us to sort of build up a concept from smaller concepts and build up much more sophisticated evaluation. All right, so let's look at a slightly different way to do, the composition, because, I'm showing you this way here with the requires expression only, but STD movable doesn't have to go here. It can go in the requirements clause instead of the expression. So I can move it up here and then just make a conjunction with the actual requirements clause. So I can refactor and move these things around. And essentially, they're going to result in the same. I can't promise you the evaluation order is going to be exactly the same. I also can't promise you, just because I don't know enough what the compiler implementations do, that these short circuit. My guess is these are going to short circuit. So like if you don't meet movable, you're probably not going to have to evaluate the rest of it. But in any case, there's different ways to move things around now that we have concepts. By the way, you can write anything in here in this. This could be a type trait here. It doesn't have to be a concept. There's advantages to putting the concepts here, but it doesn't have to be a concept. All right. So let's look at another standard library example real quickly. So this is an example of one that is, in C++ 20 derived from. You can see that it's actually composed entirely of 2 type traits. The underscore V here, of course, is your, obvious indicator that it's a type trait, basically saying that, base is derived, or derived is a base, or sorry, base is a base of derived, and that, hey, if I've got a pointer to a derived, I can convert that to base. So that's really all that's saying. I think I'm going to skip over is arithmetic and go on to ranges and concepts. So I want to sort of finish up this section with something that's a little bit more sophisticated, give you a little bit deeper insight. So of course we know that ranges is written entirely in terms of concepts. So that means I can, write some nifty code here. So, what's going on here? I have a vector, I have a predicate, which is a lambda, and I have this filter view type here, which I'm actually, I pass the range and I pass the predicate, right? And so this range for loop now only ever drops into the print part of this loop in the case where the filter actually evaluates to true, okay? So that's some nifty code. But let's see how filter view is actually defined. So here's what filter view looks like. And wow, there's a lot going on here. As we can see right off the bat, the template is constrained by other concepts from the standard library. So input range is another concept that's part of the ranges group. We have this thing indirect unary predicate, iterator T of V for the predicate. So this is the thing that says, oh, I have a function that is a unary predicate. And that's also a concept. So those concepts are lifted directly into the definition, but I also now have a requires clause, and I have a couple of additional things that I'm checking here. I've checked that the thing that I have is a view, which is actually sort of a bailout, which I'm not actually going to explain, but if somebody wants to talk about this, we can. So this is one of the sort of failure points of being able to distinguish two things just by its structure. I'll say that. And we have this is object V of predicate. Fine. So then we get this last part. What's that? Anybody got a clue what that would be? We're passing filter view to the base class. Yeah. That's the curiously recurring template pattern, CRTP, as it's well known, right? So that's interesting. So now we're seeing a use of CRTP with concepts. So what is this view interface thing? Obviously, it can't be a concept because I already told you you can't inherit from a concept. So it's a class, and it's a constrained class, and it's a base class. And it has some constraints here, which are fairly mild constraints. It just says that the derived class is actually a class, and there's some same as logic here. So that's interesting. So let's take a peek inside of view interface and let's see what it actually is. So it's got this requires clause here, just like I showed you before. And I've pulled out some very small piece of this because this base class has a bunch of functions on it, which mean that derived view classes don't have to implement all of the mechanics for a view interface. So if you want to implement a view in C++20, you derive from this type and you pass yourself in, right? So the first thing that it's interesting is because we know this is a CRTP class, it means that we can pull out the derived class definition and get a reference to a derived right in the base class. So that's very powerful because now we can use the derived type itself, in the base class implementation. And now we're going to do the thing that's the amazing part of this, which is we're going to now create negative variability in the base class, like I was showing you before with the operator star. And what are we doing here? We've applied a template function that is constrained by random access range, but it's the derived type, right? So const d, it's assigned equal to const d. So it's the same parameter here in the const form of it. And it means if this models random access range, then this function will exist. So that means that I can use an index operator only if this is a random access range. If it's just a normal range, I don't get this facility. It basically is a negative variability. It takes this method out of the base class if the range that is passed in as part of the derived class is not a random access range. So this is a super powerful technique, that can be used as part of a design, to add and remove functionality from a base type. Now, can I tell you that you can always do this and that you could write any constraint in this requires clause? Sadly, the answer is no. There are dragons here. If you have a concept that requires the type to in fact be complete at the time of the instantiation of the base class, this CRTP pattern will not work. I don't know if that's a bug or that's correct behavior. There's discussion of this in the committee. Certainly it's an example that's come up. But as you can see, the standard library has been able to make use of this facility. So it is entirely possible to use in your own design. All right, so that's the conclusion of the first part of the session. I think I got most of the questions answered. So when we come back, I think it'll be a half an hour break. When we come back, we'll talk more about writing actual concepts and dive into it a little bit deeper. And then we'll, go up the ladder one more level to actually, talking about how does it actually participate in design. I've been alluding to a lot of it up to this point, but we'll get into that even much deeper. All right. Thank you very much.